Hi there. So in this video, we're going to take a deeper look at the graphs of rational functions and more specifically look at the domain. And the domain is going to tie back into the topic that we looked at in a previous section for this unit, which was about identifying the excluded values. If you remember, those excluded values were values that made the denominator of your rational expressions equal to 0. Those are going to be values then that are going to be excluded from the domain of a rational function. So you're going to see that both graphically as well as algebraically today, okay? All right, so we're going to start here in example 1 with an equation that looks very familiar to us and build on that type of equation in order to start discussing the idea of domain, all right? So if we come down here to example 1, it says that a group of students are in the chess club and they want to rent a bus to take them to the national chess competition. And the bus is going to cost $1,500 to rent and it can hold up to 60 people. So max people they can hold on the bus, 60. Part A says examine the function for the cost per student to rent the bus if S students take the bus and each student pays an equal share. So the only thing that you're seeing here is just the new notation. Instead of in the previous section we just put a single C here for cost, but here we're just saying that the cost is a function of the number of students. So that's what that C of S means, okay? Equal to 1,500 divided by the number of students. So that's all that C of S means. It's just putting it in function notation. The function, the cost evaluated when you have S number of students. All right, so let's scoot on down then to part B. Part B and part C should be very straightforward, things that we've talked about before. Part B wants to know how much would be the cost per student if 30 students were to take the bus. So utilizing my formula here, everywhere I see an S, I'm going to plug in 30. So the cost of 30 students would be equal to 1,500 divided by 30. Can knock off those zeros. 150 divided by 3 then is going to be, 50? So we're saying then that would be $50 per student. If in part C, how much would our cost per student be if 60 students were to take the bus? So cost at 60 students would be 1,500 divided by 60. Knock off a zero there, do that division, and you should land here at $25 per student. Okay, so those are just, basic values that we can find out from our function. Now I want us to take this a one step further, and let's talk about what a reasonable domain would be for this function. How many students can we put on this bus? Okay, so I'm going to start by here. I'm going to ask you a few questions. I'm going to say, well, what is the smallest? What is the smallest number of students? I'm just going to abbreviate here. Who can take the bus? All right, so if we think about it, looking back up here at our equation, the smallest number of students that can take the bus, if I were to put 0 in for S, I'm putting 0 in the denominator, and that's a big no-no that we've talked about in this unit. You can't divide by 0. So then the smallest number of students that I can put on this bus then would have to be 1. Okay, so I'm going to answer this question then with 1 student, right? Because 0 would make my function undefined, okay? All right, let's get you another question here. What is the maximum or largest? What is the largest number of students who can take the bus? And that was actually told to us at the very beginning of the problem. If you go back up and look, when the problem was first introduced, it told us that our bus is going to cost $1,500 to rent, and it can hold up to 60 people. So the maximum number of students then that I'm going to be able to take then would be 60. So then we can say, with this information, our domain for the number of students would have to be between 1 and 60. S being the number of students would have to be between 1 and 60 to ride that bus. And I'll write it over here, S equals the number of students, which is what it was defined to be. All right, let's flip it on over then. We're going to first look at looking at graphs that are already generated for us, but what you see in these two examples below here are examples of rational functions that are already graphed. You will not have to graph those here in this class, but whenever you get to Math 171 pre-calculus, this would be the kind of graphs that you would generate for yourselves. So we're just going to be concerned today, though, with finding the domain of these rational functions. So I first want to look at it graphically, and then we will look at how to look at these algebraically as well. So your final answers when you're writing your domain will be written in interval notation. So whenever you cannot equal a value, you always use parentheses. If you can equal a value, you use the hard bracket. So I'm reminding us of that. And anytime that your graph has more than one piece to the domain, you're going to use the symbol U here to unite those two pieces of the graph, okay? So hopefully you can see here in this graph, so here's my rational function, f of x equals 1 over x minus 3. Here's the graph of it. All rational functions oftentimes have, not all of them, but oftentimes have an asymptote, a vertical asymptote. And in this case, this particular graph has a vertical asymptote here at x equals 3. And vertical asymptote are graphs that your line approach but rarely touch. I always like to use the word that my graph is going to hug those asymptotes. So what I can see then, I want to write then the domain for this function. You can see here that my graph is equaling everything but positive 3. So I could say, okay, well, x is equaling everything but 3. How do we write that in interval notation? Well, I want to then write interval notation for this leg of the graph and the right-hand leg of the graph. So this leg of the graph, remember, domain is always reading your x-axis from left to right. So this leg of the graph is coming in from what kind of infinity? Coming in from the left-hand side, so that'd be negative infinity. And then it gets right up close to 3. But it can't equal 3, so we put a parenthesis on the 3. And then the top portion of the graph picks up on the other side of 3 and goes to the right forever, so 3 to positive infinity. That is our domain there. I'm going to label that. That is your domain. Okay. Here's what I want you to note, okay, because this is going to be important for us if we don't have a graph sitting in front of us. How do we find this domain? What do you notice about 3? What does 3 do to your function? And hopefully you recognize 3 would make that denominator equal to 0. So I'm going to write that here for us, that 3 makes your denominator equal to 0. It's, in other words, our excluded value. So if you remember whenever we found excluded values back in the beginning of this unit, we set our denominator equal to 0. So here I'm just going to say set that denominator not equal to 0. Solve for x. And what we find then is that x cannot equal 3, but e can equal anything else. So what we're saying here is that I can get right up really close to it and say 2.99999. And then on the right-hand side, I can get 3.00001. Really, really close to 3, but I can never equal 3. Okay, so that's why we use those soft parentheses on the 3 there. Okay. All right, so I am going to let you then try example 2 on your own, very similar to what we've just done here in this problem. Let's flip it over and let's do one more of these graphs here together, and I'd like to look at letter C down below, okay? So here's our rational function, and it's already graphed for us, and you hopefully can kind of eyeball the asymptotes in the graph itself, right? That over here at -1 and +4. All right, so, and it wants us to identify what our domain is, okay? So I'm going to first look at it graphically, and then I'm going to go back and let's see if we can't do this algebraically, because like I said, not every time will you be able to will you have the graph sitting in front of you. So it's important to be able to do this algebraically as well. So looking at my domain here, I've got 3 portions of the graph. I've got this first portion, I've got the middle, and then I've got the right-hand side. So I'm going to have 3 pieces here to write for my domain. So remember, you always read your x-axis when you're indicating the domain. So I'm coming in from what kind of infinity on the left-hand side? Negative infinity, up until I get to that -1. So I'm getting really close to -1, but I'm never equaling it. So up to -1, that's the first leg. Then I use that union symbol to join it with the next little portion. And so that portion is picking up on the other side of that -1 and going to +4. So from -1 to 4. And then the last portion of the graph is picking up on the other side of 4 and going to right forever, so positive infinity. That would be our domain. Okay, so again, how could we find this algebraically? We would take our denominator, x squared minus 3x minus 4, and say, you can't equal 0, because if you equaled 0, you would make me undefined. And we need to figure out, okay, well, what values then would make it equal to 0? So we factor. The only way to multiply to give us x squared, x and x. Most common way to multiply to give you 4. Probably 2 and 2, but you're trying to get a 3 in the center, so let's go with 4 and 1 then. Since I'm wanting negative 3 in the center, which one needs to be negative? Hopefully you agree that 4 has got to be negative, 1 positive, and then negative 4 times positive 1, that gives me negative 4. Set both of those equal to 0. Right? Really, I'm just going to say not equal to 0 because that's what they can't equal. Solve for x in both cases. So I'm finding out then that x can't equal positive 4 and x cannot equal negative 1. Exactly what we were seeing graphically. Those are where our vertical asymptotes are occurring. My graph is approaching it, it's hugging it, and they rarely touch, okay? All right, so let's flip it over then and let's take a deeper look at, and then just by the way, once we have that information, we would translate it into interval notation down here below, okay? All right, so now let's come over to the last page and let's do the right-hand column together where we're finding the domain of each of these functions that are given to you. Okay, and again, so this time you see the graph is not given to you. So how do we find these domains? We set our denominator is not equal to 0 and solve for x. Okay, I'm going to draw a number line to give you a visual. But some of you may be able to go straight from your answer to interval notation, and that's perfectly fine. Okay. All right, so this first one here, I need to set that denominator, 4x minus 8 cannot equal 0, and I solve for x, so just a simple get letters on one side, numbers on the other, so then I find out 4x cannot equal 8, divide by 4, so I find out then that x cannot equal 2. So if I were to draw myself a number line, then I'm saying then it can equal anything but 2. So I'm going to put an open circle here at this 2, get a different color, and I can say I can equal anything but 2. So think about if you were to graph it, we would probably be looking at a vertical asymptote like we saw in the previous examples. There's also such a thing as a hole in your graph as well, and you'll talk more about that in your pre-calculus. So now I just want to put interval notation to those two pieces. So the left-hand side then is coming in from negative infinity and stops at 2. And then the right-hand side picks up on the other side of 2 and goes to the right forever, 2 to infinity. That would be the domain of this rational function. Okay? All right, let's come on down and do letter D. Letter D. X squared minus 4, the denominator, cannot equal 0. Solve for x. I'm going to pull that 4 over. So I'm going to get letters on one side, numbers on the other. So x squared cannot equal positive 4. To get x all by itself, take the square root of both sides. X cannot equal, remember you take the square root, you get a plus and a minus. So x cannot equal positive 2 and it cannot equal negative 2. So if I get you a picture this time, here's my positive 2, here's my negative 2. I can't equal either one of those values, but I can equal anything else. So there's my shading. So I want to write interval notation then. First leg, negative infinity to negative 2. Use your union symbol. And then you're going to go from negative 2 to 2. And then 2 to infinity. Final answer. Okay. And then we'll wrap it up here with the last one on that column. I am going to set that denominator not equal to 0. So 2x squared minus 3x cannot equal 0 and solve for x. This is going to require me to factor because those two terms have something in common. Have an x in common. Write what I have left over. So 2x minus 3. Set both of those equal to 0. So since they both have letters, so x cannot equal 0. 2x minus 3 can equal 0. So the first one's already solved. The next one, I'm going to pull that 3 over. 2x cannot equal 3, and then divide. X cannot equal 3/2. So then I've got my 0 and my 3/2. I'll just put an open circle on both of those. I can equal anything but that, so there's my shading. And I want to now put interval notation to that shading. So negative infinity to 0, 0 to 3/2, and then 3/2 to infinity. And that wraps that up, okay? All right, I definitely encourage you to finish up this section and check yourself by the solution key. Thanks a lot. Bye.